In an AC circuit, capacitors and inductors consume no power. They store electrical energy, but when the current reverses direction, they give that energy back. So power is only consumed by a resistor because a resistor will heat up and convert electrical energy into heat. Or if the resistor happens to be a light bulb, it can convert some of that energy into light as well. So the average power consumed by a resistor is equal to the average current, or the RMS current, times the resistance. Or we can use the expression that the average power is equal to the RMS current times the RMS voltage across the resistor. So if what you know about the circuit, instead of knowing the voltage across the resistor, if instead you know the voltage of the power supply, and you know how the relationship between the voltage and the current, so you know how the voltage either of the power supply either leads or lags the current, that will give you the phase angle, and then you can use the voltage of the power supply times the cosine of that phase angle to get the voltage of the resistor. So the cosine of theta is sometimes called the power factor because it tells you about how much of the voltage of the power supply is equivalent to the voltage across the resistor, and allows you to find then the power consumed by the circuit. RLC circuits can undergo resonance, and this happens, and we can see why this happens if we look at this formula for the current. So if we look at the current in the circuit and we think about when is the current going to be maximum. So before we saw that the voltage across the power supply is equal to the RMS current times the times Z, and we know that calculating the impedance, Z, is equivalent to the square root of R squared plus the difference between the two reactances. So if we look at this expression and ask ourselves the question, when is the current going to be maximum? The current will be maximum when X sub L is equal to X sub C. Remember, both of these quantities depend on the frequency. So we can adjust, if we can adjust the frequency of the power supply, we can find a special frequency where they are equal to each other. Then this term becomes 0. The stuff on the square root is as small as possible, so I will be as big as possible. So we get the maximum amount of current in our circuit when we adjust the frequency so that the capacitive reactance is equal to the inductive reactance. If we write out what each of those quantities are, we can then solve them for the frequency. And we find that the frequency that causes this resonance condition when IRMS is maximum is equal to 1 over the square root, or 1 over 2 pi times the square root of the inductance of the inductor times the capacitance of the capacitor. So this is the resonance frequency of an RLC circuit. This is actually used in radio tuners, in some kinds of radios. You can have an inductor, for example, that you can change the length of, and then by changing the length you can control the inductance of the inductor and tune it to hit a certain resonance frequency. So if you're trying to make your radio sensitive to just one frequency, then you can adjust the inductor so that the resonance frequency matches the frequency that you want to pick out with your radio, and then the radio will be most sensitive and will start to resonate and have a stronger current when that frequency is sensed by the radio. Transformers are devices that change the voltage of a current. So if we have transformers, you can see them out on telephone poles, and their job is to take high voltage and step it down to lower voltage. The reason why we use transformers is because transmitting an electrical energy at higher power or higher current, transmitting electricity at higher voltage is more efficient. So the community will have some power demand. They will need a certain amount of electrical energy that they are using, and we know that power is equal to current times voltage. So if we solve that for current, we can see that the current that is needed is going to be equal to the power demand divided by the voltage. However, wires are not perfect conductors. They have some resistance, even though it's small, and so the wires will heat up a little, the ones that are used to transmit this power, and so there will be some power that is lost. And the lost power is equal to the current squared times the resistance of the wires that are used to transmit the power. So the current we found that we need is equal to the power demanded divided by delta V, so we can put that in for I, and then we can compute the ratio of the power that's lost over the power that is demanded. And we want this ratio to be as small as possible because then our transmission will be efficient. So if we divide both sides of this expression by P demand, we see that the ratio of the loss over the demand is equal to the power that's demanded times the resistance, and then divided by delta V squared. So if we make the voltage that we're transmitting power with very high, we will have more efficient transmission and we will have lower losses. However, high voltage is dangerous. So when the power is brought to your house, it then needs to be stepped down to a lower voltage. So the way that transformers do this is that they use inductance. So you will have two coils of wire, one that is at the high voltage that's supplied by the power company, and then there's some soft iron inside the transformer that helps conduct the magnetic field, and then a second coil which is connected to the wiring that ultimately ends up in your house. And so this will be at a lower voltage. So you have high voltage over here, and you'll have a lower voltage in the secondary. So the primary, this is AC current, and so since it's AC, it's always changing, and so the magnetic field that it makes, because you have a current in a wire, that magnetic field is always changing, so the flux through this loop is always changing, and so it will always be inducing a changing AC current in the secondary loop. So none of the electricity actually travels directly from the power company into your home. It first goes through this transformer where it becomes a magnetic field, a magnetic flux, and then gets changed back into the current that goes into your home. Now all of this is inside the transformer, because the transformer looks kind of like a bucket on the pole. All of this is surrounded by some sort of oil which kind of cools everything and makes sure that nothing rusts, and then that's surrounded by the can that protects all of it. So you can see that a transformer is an incredibly simple device, and this is another reason why AC power is used in our homes. One, it's very easy to make. You spin a coil of wire in a magnetic field, a generator naturally makes AC power, and then it's really easy to convert from one voltage into another using this passive transformer, which just sits there and lets the magic of magnetic fields do all the work. So looking mathematically at what's going on here, we can use, since we know we're dealing with some magnetic induction, we know that we can use Faraday's law. So the induced EMF, or the EMF in coil 1, so this first coil, is going to be equal to, well, you can see using Faraday's law, that voltage is going to be equal to the number of turns in coil 1 times the changing flux with time. And that same flux, so that same flux that this one generates, is going to be passing through coil 2, and so that would be equal to the number of turns times the flux with time in coil 2. So the flux, since this flux is the same, we can solve both of these equations for flux, and then that would be V over N, so we would have V1 over N1, and that's going to be equal to the flux, which is also equal to V2 over N2. And so then we can change this equation, solve it for V2, and we can see that the voltage in the secondary coil is equal to the ratio of the number of turns in each of these two coils times the voltage in the primary coil. So we can control the voltage drop or the voltage gain by the relative number of loops. In any case, the current times the voltage in the primary and the secondary coils are the same. Power in is equivalent to power out. So next, let's consider this question. The primary coil of a transformer is connected to a battery, a resistor, and a switch. The secondary coil is connected to an ammeter. When the switch is thrown closed, will the ammeter show zero current, a non-zero current for a short time, or will it show a steady current?